Hello, this is Dr. Grande. Welcome to my video on conducting a MANOVA in SPSS. So a MANOVA allows us to look for differences across several dependent variables. Right, so in this example I have here, and these are fictitious data, we have an ID variable, we have an independent variable, and there's three levels to this independent variable. And let's say that this research project, these data are collected from looking at a substance use facility, let's say specifically treating alcohol use disorder. So they're going to have treatment as usual, which is one of the levels of this independent variable program. But you want to add an individual treatment, some sort of specialized individual treatment, or group treatment. So you have individual, group, and treatment as usual. But notice we have two dependent variables. One is functioning. So for this scale, let's say the lower value indicates higher functioning. And then we have quantity. And this would be the quantity of alcohol consumed, say, during a period of a month. And of course, a higher quantity would not be what we'd want. That would indicate a less successful outcome. So what a MANOVA does is it creates a linear combination of these two, in this case these two dependent variables, although you can have more than two. And it tests to see if there's any differences across the levels of the independent variable on that linear combination of the two dependent variables. So it lets you detect differences across the levels of the independent variable on that linear combination of dependent variable, but until you look in further, you won't know where those differences are. So it's a linear combination. It's not one variable or the other where you're going to see the difference. It's the combination of the two. So there are some follow-up tests as part of the MANOVA procedure, and in those you can see, was the difference on the functioning dependent variable or on the quantity, or was it on both? Or was there no difference? Did all three treatments work equally as well on the linear combination of the two dependent variables and on each dependent variable separately? So before we get started and running the MANOVA, I want to go over the assumptions. I'm going to show you how to test for the assumptions of MANOVA. And there are a few assumptions for this particular statistic. You do need two or more dependent variables, and they have to be measured at the interval or ratio level. SPSS refers to those levels collectively as scale. So if you look here in the variable view, there is no choice for interval or ratio, you just have scale. So that means it's either interval or ratio. Let's assume in this case that functioning is interval and quantity would be ratio. But again, there's no way to distinguish between the two in SPSS. They're both treated the same. You need to have at least one independent variable, and you can have more than one. And that independent variable must have two or more categorical groups. And you can see we meet that assumption with program. We have individual therapy, group therapy, and the treatment as usual. The observations need to be independent, and you need to make sure you have a sufficient sample size. And specifically, you need to have a minimum number of samples for each level of the independent variable. Now there's different opinions about what the minimum should be. One common minimum used is 20, so you'd need 20 sets of scores on these dependent variables for each level of the independent variable. As you can see in my case, I only have 15 in each group because I only have 45 total. Another opinion is that the quantity for any one level of the independent variable needs to be greater than the number of levels of the independent variable multiplied by the number of dependent variables. So if we have 3 levels of this independent variable and we have 2 dependent variables, that would be 6. So if we're looking at it that way, we do meet the assumption of sufficient sample size by level of the independent variable. MANOVAs assume multivariate normality. They are sensitive to outliers. There needs to be a linear relationship between each pair of the dependent variables across each level of the independent variables. This test also needs homogeneity of covariance matrices, but that assumption is tested as part of MANOVA. And the dependent variables in a MANOVA cannot be multi-collinear. So let's first test for outliers. We're going to do that with a linear regression in this case. It's going to be analyze, regression, linear. And for this test, the independent variable in the MANOVA is actually the dependent variable, because we're testing an assumption here. This isn't the MANOVA, this is a linear regression. So the independent variable will become the dependent for this test, and both quantity and functioning, which are the dependent variables, will become independent variables here. And everything here will stay as default except for under the save. I'm going to create a new variable, and what I want is the Mahalanobis distance. Right, so it's this box here, Mahalanobis, and this will create a new variable. So I'm going to click continue and then OK, and you can see that it conducted a regression here. But what we're interested in is at the end, under residual statistics, we want to have a look at the maximum value for the Mahalanobis distance, and that is 5.634. So now we have this value here, 5.634, and what we need to consider is the maximum allowable critical value for Mahalanobis distance. And there are critical value tables available for this, but for a MANOVA with two dependent variables, the maximum would be 13.82. That would be the maximum value. Anything above that would be an outlier. For three dependent variables, it's 16.27. So here we have two dependent variables, so we know it's 13.82, and we can see that we do not have any values that exceed 13.82. Now say this maximum value did exceed 13.82. If you want to identify the outliers quickly, you would go to Data and Sort Cases, and you would sort the Mahalanobis distance, and you'd sort it descending. Right, so you'd bring the larger values to the top. So if I sorted this, you can see that there is our maximum value, and at the bottom is our minimum value. And of course, to return that back to the way it was, you would just go to Sort Cases. In this case, I have an ID variable, which I try to always have an ID variable, and you would move that into Sort By, and you would leave it as ascending. And now your data set's back to the way it was. So now that this is tested, we could clear this variable, but I'm just going to leave it up. And now we're going to build a scatter plot. So I'm going to go to Graphs, Legacy Dialogues, all the way down to Scatter Dot, and I want the matrix scatter here. And then it's going to, I have three choices. One is define, so I'm going to define. You can see I've already populated these variables, but I'll show you what I did here. It's functioning and quantity to matrix variables, and program to the row list box. And I will make a change under options. I'm going to exclude cases variable by variable. There are no missing cases in these fictitious data, so you don't have to worry about it here. But if you are missing values, you do want to exclude cases variable by variable for this analysis. So we'll click OK. And what we're looking for here is an elliptical pattern generally moving from the bottom left to the top right. And as you look at these 6 different plots, you can see that is the general pattern. So we're pretty good here. If you see kind of a square, then you're violating the assumption of that linear relationship. But here there does appear to be a linear relationship for all 6 of the plots. Another assumption is the multivariate normality. And the way that's often tested is by looking at the normality for each of the dependent variables. Now that is a different thing than multivariate normality, but that's how we typically test it. So we'll go to Analyze, Descriptive Statistics, Explore, and you can see I have this populated, so I'm going to reset this. So it's just going to be functioning and quantity over to the dependent list, and then under plots we're going to want to check off normality plots with tests. And I don't really use the stem and leaf too much, but I will check off the histogram. So let's run it this way and take a look at our results. What we're most interested in here would be the value, the significance level of Shapiro-Wilk. So if it's greater than 0.05, we're going to assume normality. And if it's less than 0.05 or equal to 0.05, we're going to assume that we have a non-normal distribution, that variable. So we can see that we are violating an assumption here. Potentially, again, this is multivariate normality that we're supposed to be testing, and I'm testing univariate normality. But we can see that we have to reject the null hypothesis here on quantity, so we do not have a normally distributed variable there, and or we're going to assume we don't, and then functioning we do. So let's now move to the assumption of no multicollinearity. So the way we test this is through correlation. So we're going to use bivariate correlation. And again, you can see I've populated this. I'll reset it. Just functioning and quantity get moved over to the variables list box. Under correlation coefficients, the default is Pearson, and I'm going to leave it set there. And there are no other changes, so I'll click OK. And you can see we have a correlation between these 2 variables, the 2 dependent variables, functioning and quantity, of 0.339. So the assumption I'm testing is that we don't have multicollinearity, and that's defined in a few different ways. One cutoff is 0.9, so if the Pearson's R value is greater than 0.9, then the variables are multicollinear. Another cutoff is 0.8. But we also have to make sure that there is enough of a relationship between the 2 variables. So it's not just the absence of multicollinearity that we're looking at here. We also want to make sure that there is a relationship that meets a certain level. And generally we say above 0.2. So here at 0.339, this is acceptable. So we've met that assumption. So with our assumptions tested, let's move to the MANOVA, and that'll be Analyze, the general linear model, and multivariate. I'm going to reset this. So here, the dependent variables, remember this, the MANOVA handles multiple dependent variables. That'll be functioning and quantity, and the fixed factor, the independent variable, will be the program. Note that there's also the ability to add a covariate. If you were to include a covariate, that would make this analysis a MANOVA instead of a MANOVA. So looking at our buttons here to the right, the model is going to stay the same. Contrast, just to show you how this works, I'm going to add a simple contrast, and you can choose the reference category. You have a choice, last or first. So if you're looking at an analysis like this, we're really comparing individual therapy and group therapy to treatment as usual. So it makes sense for the reference category here to be the last level of the independent variable, which is treatment as usual. So I'm going to leave that as last, and make sure here you click change. So you can see program simple. Plots I'm not going to change. Post hoc. Now we don't know if we're going to get a significant value any time we enter into running MANOVA, but in case we do, we're going to set this up for Posthoc Test of program. And because all my group sizes are equal, I'm going to use Tukey. If I had unequal group sizes, I would use Shefe. So I'm just checking Tukey after moving program over to the Posthoc Test 4 list box and clicking continue. Under save, there'll be no changes. And under options, I'm going to move program over to display means 4. I do want homogeneity tests, descriptive statistics, effect size, and observed power. Click continue. So now this dialog is configured for MANOVA. I'll click OK. And you can see here are 3 levels of the independent variable: individual, group, and treatment as usual. And as I mentioned, the sample sizes are the same for each group. They're equal, 15. And then taking a look at the descriptive statistics, you can see that for functioning, it does appear that the mean is a bit lower here for individual, and it's higher for group, and then even higher for treatment as usual. And then for quantity of alcohol consumed during the month, we can see that individual, again, is the lowest. Group is lower than treatment as usual, but not quite as low as individual. And then, of course, treatment as usual is the highest. And of course, remember, this analysis is based on fictitious data. All right. So moving to Box's test of equality of covariance matrices, we have a significance here of 0.781. So we have met this assumption because any significance value here greater than 0.001 would meet the assumption. So no problems there with the boxes M. Then we'll move down to multivariate tests. So as you can see here, there are 4 different values that you can interpret, and we're only going to interpret one. And a common way to select which of these we're going to use is based on whether we have met the assumptions for MANOVA or not. So if all the assumptions have been met, and in this case I would say that we did not meet all the assumptions because there's some uncertainty regarding normality, we would select Wilks. So if we have met all the assumptions, we select Wilks lambda. If we have not, it's Pillai's trace. So in this case, I'm going to go with Pillai's trace because of that Shapiro-Wilk result. And you can see here we're at 0.026. So we have statistical significance even using Pillai's trace. So what we're saying here is that there is a statistically significant difference across the levels of the independent variable on a linear combination of the dependent variables. We don't know where that difference is. We can't speak yet as to whether it's on functioning, quantity, both, or neither. But we know that across the linear combination, using a linear combination of dependent variables, we do have a statistically significant difference between the levels of the independent variable, which were individual and group counseling, and then treatment as usual. So those groups are different on that linear combination. So let's take a look little further down and get some more detail. Now we do want to interpret Levene's test of equality of error variances, and in this case we have a non-significant result for functioning and for quantity, so we're good. We would worry if we were at 0.05 or below. But with these significance values, we're in good shape. No cause for concern. And now we have tests of between subjects effects. Right, so we want to look at program. So don't worry about corrected model intercept. We want to start here at program. And first we'll look at functioning, and we see there is a statistically significant value here, 0.005, on this dependent variable functioning, and there's not a statistically significant finding on the variable quantity. So moving down a little more, we get to the contrast. Remember, I ran the simple contrast with the reference category as treatment as usual, which you can see it indicates here the value 3, which is the value assigned to treatment as usual. And you can see between level 1 and level 3, we have a statistically significant difference on functioning, not on quantity. And between level 2, which would be group, and treatment as usual, non-significant result on both. So we have the multivariate test results again here. I will point out, which I didn't note before, the partial eta squared. So if you move up, you see here it's 0.122. And you can see it was the same here. Right? That indicates that 12.2% of the variance in the dependent variables can be explained by, in this case, the treatment. The independent variable, in this case, is the treatment. So moving down to univariate test results, we can see that just looking at functioning, we do have a statistically significant finding, and we don't with quantity. And you can see quantity is explaining very little movement, very little variance in the dependent variables, 6.4%, whereas functioning is explaining 22.4% of the variance in the dependent variables. Again, we can see the means here, and we will interpret the post hoc tests because we had a statistically significant finding on Play's trace. And similarly, because of that, we were able to interpret these univariate test results. So looking here at the post hoc test, this was a 2-key test. You can see individual to group. Right, so the differences between the individual level and the group level of treatment, non-significant, 0.059. The difference between the individual and treatment as usual levels of the independent variable was statistically significant, 0.004. So there's a statistically significant difference between the individual level and the treatment as usual level on the functioning dependent variable. And then looking at group and treatment as usual, we have a non-significant finding. So then looking at quantity, which is the other dependent variable, we have a non-significant finding between individual and group, non-significant between individual and treatment as usual, and non-significant between group and treatment as usual. So kind of an overall interpretation in terms of the analysis, the MANOVA that we ran. Well, we have a statistically significant finding here with functioning just between individual and treatment as usual, but no other statistically significant findings. So it does appear that the individual therapy is more effective than treatment as usual, but only for one of the two dependent variables, only for the functioning. I hope you found this video on conducting a MANOVA in SPSS to be helpful. As always, if you have any questions or concerns, feel free to contact me, and I'll be happy to assist you.